It's my great pleasure to introduce to you Dr. Philip Kegelmeyer. Philip graduated from Stanford in 1985, and he is currently a distinguished member of the technical staff at Sandia National Laboratory in Livermore. He leads the data discovery program within the Advanced Simulation Computing program. And then I'll let him tell you what he's going to talk about.
Great. Thanks, Wendy. And I should, so thanks for the introduction. I'd also like to add, does this sound okay? Is there any feedback back there? OK. So I'd also like to add that one of the projects at Sandia I most enjoyed was acting as semi-mentor to Wendy and helping to draw out the mad skills that unfortunately landed her at Google. Have to rethink my mentoring strategy. OK, so one thing I'd like to say is that this is intended as an overview talk, but some of the concepts are weird and counterintuitive, even to people who know the field. So I've made a stab at practicing a couple times, but I really do encourage questions. And so please feel free at any point to stop and raise your hand and ask. In fact, if I don't get a question by the time that I start claiming that degrading your data improves your accuracy, I may actually just pick somebody at random and ask them to ask me a question. OK, so I'm sure most of you are quite busy. So I'm going to start with my conclusion, or at least an initial release of it. And since this is a talk of advocacy as well as information, that conclusion is, if you use supervised machine learning, use ensembles. And that's it. If you are willing to trust me on this, you can go download my talk. I have a how to get started slide. And you're good to go. If you want to hear more, I'm going to start by expanding on the terms in blue. And in fact, that'll be the motif through here. Every time I bring up a new concept, it'll be in blue. And that's an implicit promise. I'm about to explain what I'm talking about. So what is supervised machine learning? What am I going to be talking about today? OK, there's all kinds of data mining. And Google, of course, should know that very well. The specific kind I'm talking about is looking at past data in order to be able to predict things about future data. In particular, looking at past labeled data in order to label data that you don't yet understand. So the word supervised and supervised machine learning means exactly that. We have some sort of prior training data that's going to supervise the learning process. So I've entirely invented an example that I'm going to be reusing throughout the talk of what a machine learning project at Google might look like, where the data is a query and its response. One of the things you need to know in the training data is the truth, the label, the thing you're trying to predict. So in this particular case, it's a binary value. Either that response was or was not relevant to the query. And then the rest of the data that you work with are attributes, measurements that you can make on the question-response pair that theoretically have some connection to whether or not that was a relevant response. So these are all entirely invented attributes, entirely invented numbers. Maybe freshness is how recently the response page was crawled. Maybe distinctness is a function of how unique that particular set of query words is, or something. This is all invented for the sake of clarity. But the point is that in the rows, we have data that we're learning from, and we have a lot of it. In any real problem, capital N in any real problem is thousands of examples. And we could have many, many attributes. What's going on with machine learning, with all the machine learning algorithms, is that it's believed to be that there's some sort of function from the attributes to the truth. And the point of the machine learning algorithm is to discover that function, or at least to build an estimate of it. And then you use that function to label new data that you don't know the truth about. So a geometric way to think about this, at least for numerical attributes, is to think of an n-dimensional space where there's a dimension corresponding to each of the things you measure. And so each data point you have sits somewhere in that n-dimensional space. And I've drawn a very, very simple two-dimensional case in the upper right corner where I've got two attributes, x and y. And I've only got two kinds of things, blue circles and red x's. And the fact that I'm showing them as blue circles and red x's for this means that this is training data. This is data I know the truth about. So you can think of any machine learning algorithm as an attempt to partition this attribute space. And once you have partitioned it and assigned a unique label to every partition, well, then when you need to label some new data, you just take that point, plop it into your attribute space, figure out what partition it fell into, look up the label of that partition, boom, you know whether or not that query is predicted to be relevant or irrelevant. Okay. I exclusively use decision trees to analyze. Oh, question.
You're assuming this is time invariant?
That's a very good question. I'm assuming that either the data is time invariant or fixed in time, or that there are attributes in the data that measure something about your thing that captures the time question. So it's quite often that you'll have this process that it changes over time, and one of the attributes will be a running average over the last n samples or something similar. There are other ways of dealing with time varying data that I'm not going to get into, but that's one of the core approaches. I'm sorry, and the question was, how do you handle time varying data? Okay, so I exclusively use decision trees for reasons I'll try to discuss later. But other pattern recognition algorithms you probably have heard about are neural nets, support vector machines, k-nearest neighbors, naive Bayes. There's a whole slew of algorithms, and probably there are some new ones being invented every day, every time you get an ambitious professor at a university somewhere. Okay, so that's machine learning as a black box. Except for one bit of advocacy about decision trees later, I'm not going to go into the details of how machine learning algorithms go about predicting, figuring out what this partitioning is. I'm also not going to be explaining applications of this. I mean, you know, presumably you have situations where you want to predict the future based on the past, or you can imagine them. What I am going to be doing is telling you, regardless of what machine learning algorithm you use, how you can make it better. Great. And to do that, I first have to tell you the traditional way of doing this without using ensembles, which is the magic trick that I'll be explaining. The traditional way of doing this is you take all of your data, and you feed it to your favorite algorithm, and you build, let's call something I'm going to call a sage for sake of comparison to something else later. So the sage sees all of your data. Just to clarify one possible misconception, the sage is not thereby perfectly accurate, because there are many problems for which, even if you have perfectly sampled training data, you can't get a perfectly accurate decision surface. In this particular case, I have a mixture of Gaussians. I've got two different 2D Gaussian distributions. I've sampled for one to make red dots. I've sampled from the other to make green dots. The optimal decision surface is the light line in blue. If you're in the upper left corner and you see a new data point, you should call it red. If you lower right corner, you should call it green. And that optimal decision surface achieves what's called Bayes' error, which is the best possible error you can achieve for a given data set. But it's non-zero. So even if you had all of the data you could possibly want, you can't do any better than Bayes' error. But in theory, if you look at all the data and you build a sage, that's as good as you can do. But that theory is wrong. Because you can do something very counterintuitive, and this is the first of the weird things, and improve matters. You can degrade your data. I'll explain in more detail exactly how, but the core idea is I have this pile of training data. I sample from it to make another, with replacement, to make another training set the exact same size. So my new training set, let's call it a bag of data, is a degraded version of the first training set. It's missing some points. Some points have been duplicated or triplicated. I build a single classifier from that new bag. I get something I'll call an expert. Now, as you can imagine, the individual expert is less accurate than the sage, because it's seen a degraded version of the data. The magic is that I do that again. I make another expert using another random sampling. I make another expert making another random sampling. It turns out that it's provably the case that if I combine so if I have a new data point to analyze and I show it to the sage, I get a classification. If I show it to the crowd of experts, let them all vote on a classification, and I take the majority vote of the experts, it is provably the case that the majority vote does no worse than the sage, and in fact, in practical problems does much better, and in fact, even more practically, the more difficult your problem, the more ensembles help you. The only place ensembles don't help you is when you have a fairly trivial problem that the sage could do fairly well on in the first place. Yes?
It's a continuous problem, so what do you mean by majority vote?
So for majority vote, I mean if I have 100 experts and I've got two classes, relevant or not relevant, right? I'm sorry, the question was what I mean by majority vote. And I don't have to talk to that. The question was, what do I mean by majority vote? And the answer is, if I have 100 experts, I'll let them all say relevant or not relevant. If 70 of them say relevant, 30 of them say irrelevant, then the opinion of the crowd is that it was relevant. And that's the final classification. In the back, yes?
So what's the difference between the set of experts and the fancy
Well, I'll expand on that. It's the nature of the data that the experts individually see, and I'll be expanding on that next couple of slides.
If you're trying to predict a continuous value, can you vote with averaging? Does that also work? Are you going to talk about that?
I'm not going to talk about it, but it does work. You have to use a mechanism that will give you a continuous value. So you have to use a regression tree of some sort. But you can, in general, for a broad class of problems, make that work. OK, so the question is, from the back, how exactly does this work? I'll illustrate. Remember again that this is the unaltered data. This is all the Google queries. I've got capital N of them. Like I said, what you do is to make the first bag, you sample with replacement and make another bag the same size. So this is the first sampling, building the first expert. Looking at this, you can see that, for instance, query 2 and query 4 were repeated. Query 3 is missing entirely. Again, this is all entirely invented examples for the sake of pedagogical explanation, but this is basically how it works. So I have a degraded, altered version of the original data. To make the second bag, I start the process over with a different random seed. So I get a different set of sampling. In this case, I'll have Q3 repeated and Q4 and others are missing. Each time I do this, I build an expert. And that's how you get the variety of experts. This technique, in fact, is called bagging. This is another schematic I'm going to return to, partly because bagging suggests bags of data, but it's also a back formation from bootstrap aggregation, which if you've studied in statistics world, is the idea that gave rise to this idea in the first place. This whole concept of bagging came up in the middle 90s, was first largely spearheaded at least by a guy named Leo Breiman at the University of California, Berkeley. OK, so let me explain this schematic, because I'm going to be using variations of this to explain what other variations of ensemble methods look like a little later in the talk. The core idea is in the first iteration, I have all the data in the first column of the first iteration. And then I have a sampled set in the second. So here, I've sampled from this set to make this set. So I've got 2 cases of 1. I'm missing 4, and so forth. Over here, to get from, again, I have all of the data I'm sampling from. I get 2 6s, I'm missing 5, and so forth. This is basically just another way of looking at the exact same resampling information I was presenting a moment ago. Yes?
Can you vary how much graded the samples are, or are they all graded so it's the same amount?
So you can do, so the question was, can you vary how much you degrade the samples? The short answer is yes. And in fact, there's a zillion different ensemble algorithms that explore various ways of degrading data, and I'm going to talk about a couple of them. A longer answer, which I'll also get to, is that you have to be careful about that, because it turns out almost all of them have the same accuracy, but that can be easy to miss. One of the beautiful things about ensembles is they tend to flatten performance between lots of different behaviors, lots of different algorithms, which removes some of the design stress of building your machine learning tool. You don't have to have the exact right neural net architecture. You don't have to have the exact right pruning strategy for your trees. If you use ensembles, everything goes to the same mean. And I'll explain that in a little bit. Question in the middle there.
What's the purpose of preserving the set size rather than just, if you're going to toss some, why not just toss them? Why replace them with repeats of others?
OK, so the question is, what's the point of maintaining the set size? And there's 2 answers. One is that it turns out for the broad class of algorithms, I'll come back to that question, and I will make a note to do so, because that will make more sense when I later talk about diversity. And there was another question, yes?
How do you choose the number of experts?
I'm coming back to, I'll come to that too later in the talk. Great, thanks. These are all great prompter questions. And the question was, how do I choose the number of experts? OK, so this is bagging. So before I answer all these practical questions, I'm going to address a little bit why the heck this would work, because I've just told you that a crowd of experts in concert is smarter. A crowd of less accurate classifiers in concert is smarter than single sage. Well, this is still grist for grad students at various universities. And if you have a good idea, you can probably get a PhD thesis out of this. But the general theory has begun to converge around 2 ideas. One of them is the Bias-Variance Model. And to explain that, I'm first going to explain it not in the context of machine learning, but just in the context of linear regression, because it's easy to illustrate. The idea is this. If I have a bunch of data points, those blue X's, from a real curve that I don't get to know, how can I estimate that real curve? In the regression world, you say, fine, I'm going to apply some sort of regression. But you have to choose the order of your regression when you do so. If you pick a linear regression, which is what the top right illustrates, and you've got a binomial curve, a quadratic curve, then you're going to get a bad fit. And you're always going to get a bad fit. There's no way to do any better. Unfortunately, you can go wrong in the opposite direction, which the bottom right illustrates. If you pick a too high order of polynomial to fit your curve, then by golly, you're going to fit every single point that you've got to sample with. But you've overfit. You've also missed the true shape of the curve. The genius of ensembles is to realize that you can't fix the first problem, but you can fix the second. Because if I take a different subset of those points and have an overfit curve, I'll get a wildly different curve. If I do it again, I'll get a wildly different curve. But if you average them, you begin to converge to the true curve. And this has actually been known in the regression world for a very long time for just pure graphic stuff. That's the core idea of what's going on with machine learning stuff, is that each individual model, each individual sage, is an approximation of some real function, but it's always an imperfect approximation. Just one second. And because you're dealing with real sampled data. So you average the approximations, you do a better job. You have a question?
Okay, so let's say I did the ensemble on the second curve, and I go to the extreme, and it's just 1 point. And each expert just look at 1 point. So I'll get a whole bunch of horizontal lines.
Okay.
I average them to get a horizontal line, and that's the ensemble answer.
That's true. So I mean, this is an analogy. Excuse me. The point was that you can't push this analogy to its limit case because if you average a bunch of impulses, for instance, or individual points, it's just not going to give you a good result. And that's absolutely true. This is just an analogy designed to build confidence in the overall way ensembles work. I mean, I guess the pattern recognition equivalent would be if I built a one-class classifier for every point in my training data. That's not going to work very well, but that's recognizing people don't do it. What's more,
But you said you have a proof that it always works.
Yes, there is a proof, but it's not based on this theory, and it's not my proof. You can look it up. I actually have a page of references, the last slide of this talk, that substantiates everything I say. And in fact, every time there's a little bracketed reference mark that's pointing at one of those papers. Okay, so. Here's another way of thinking about why ensembles help. Imagine a test problem in which each member of the ensemble, each expert, is really, really inexpert. It's only 10% accurate, which means 10% of the time it really knows the right answer and it votes for the right answer in a 3-class problem. But the other 90% of the time, it hasn't a clue, and it picks one of the 3 classes at random. Well, if I have 100 of these experts, in fact, if I have 10 of these experts, the crowd of experts is perfectly accurate, even though each individual expert is only 10% accurate. Because, let's say I have 100. Of that 100, 10 of them are going to know what's going on, are going to correctly vote for yellow. The other 90 are going to be clueless, but 30 will vote for yellow, 30 will vote for blue, 30 will vote for red. The majority vote will say, I've got 40 votes for yellow. Yellow wins. What's happened is that the people who are wrong have canceled each other out. Now, this only works if the members of the ensemble have the property that once they're wrong, they're randomly wrong. That's really hard to achieve in both in computer science and also in the real world. And so a lot of the most fertile research in the last few years has been about how to go about achieving this property. Because as you can imagine, it's a little tricky. What you're trying to engineer for is a situation where your classifier is as accurate as possible. But as soon as it stops being accurate, it doesn't degrade gracefully, it degrades terribly, it immediately becomes random. It's also the case that accuracy is a point property that each individual classifier has, but diversity is an emergent property of the ensemble. And since the classifiers are built individually, it's really tough to come up with a system that will make an individual classifier diverse, because it's not even well defined until you look at the ensemble. But if you pick your algorithms correctly, you get primarily diverse methods, and that's part of what I'm trying to talk about today, is to talk about how to pick those algorithms correctly. Another point to make is this. This is not social cultural diversity that's helping you out here. In fact, it's the inverse of it. I mean, one of the things that you hear about in terms of putting together a problem-solving group is you want to have as many viewpoints as possible in the room, because that ups the odds that at least one person in the room will have a handle on the right answer. That's not what's going on here. What you're hoping for is that you want people to be diverse in their mistakes. So where this is actually showing application is that people have studied various ways of having groups of humans make decisions in such a way as that they don't get to know what errors other people are making, to avoid this process of people group thinking their way to the same wrong answer. People in the intelligence community study this, people in other contexts study this. There's a whole psychological field, which I know a little bit about, but not a lot, which is devoted to the principle of making humans as diverse in their errors as possible, to avoid everybody jumping on the same sheep following the same leader kind of error. Okay, so that's supervised machine learning and the basics of ensembles in a nutshell. Those of you who know anything about machine learning may be wondering, why I haven't mentioned boosting, which is the golden hair child of ensembles. And so I am going to mention boosting, if only to warn you against it, or to suggest that if you do want to use boosting, that you use a less dangerous algorithm called I-voting. So here's my first iteration of my conclusions. In general, if you're going to use supervised machine learning, use bagging. If you really have clean, well-behaved data, you can perhaps safely use I-voting, which is a variant of boosting, but you actually probably don't have data that's as clean as you think you do, and boosting will hurt. But to explain all that, I have to explain what boosting is. So I'm going to start by explaining boosting, and then explain what the I-voting variant is. Okay, so here's the core idea of boosting in the same schematic as bagging. In the very first iteration, for the first expert on the far left, it works the same way. Now, what the colors mean is the colors are the weights of the samples, and the higher the weight, the more likely the sample is going to be picked to be stuck in the bag. With bagging, you pick everything with uniform probability. The main variant in boosting is that now I'm going to pick according to my current weights. So in the very first iteration, everything is weighted the same. My first bag is just like a regular bag. But what you do then is you say, OK, for any stage I am, if I'm in the third stage, I take my original data, I show it to the ensemble I have so far, and I find out how wrong or right I was for each sample. The more wrong I am, the greater weight I give to that data point. So that's what the colors are supposed to indicate. The darker reds are getting you to a situation where you're getting that particular sample is difficult for some reason, is resisting analysis, you keep getting it wrong. The ones that are getting mellower are ones you're easily getting right. So what happens at every stage here is that the boosting algorithm focuses on the tricky cases. In fact, it over-focuses, which is why the other variant, the other difference in the schematic is there's now weights on each of the experts. And the boosting algorithm, you can Google it in a heartbeat, tells you all the details, but basically the weights keep you from putting too much weight on the experts as you go down the line, so that you don't over-focus on the problem. And there was a question.
Does it mean like boosting is sensitive to outliers?
I'm sorry, I can just barely hear you. I'm sorry.
Does it mean like a boosting algorithm is sensitive to outliers?
Yeah. So the question is the boosting algorithm sensitive to outliers? And the answer is absolutely yes, and that's the source of my concern. Well, yeah, I'll come back to that. There we go. So the way. So this is just illustrating what I was saying a moment ago. What boosting does for you, and the reason it looked attractive at first, was that it tends to focus you on the difficult cases near the border of your decision surfaces. So once you use boosting, you stop paying attention to the red dots in the upper left corner and the green dots in the lower right corner, because those are easy. You take more attention, you throw more CPU cycles at the places where you have a border. So this is why boosting works, but as the questioner pointed out, boosting also works too hard. It's just like a regression, overfit regression, in that it really does everything it can to correctly classify the points. And because this property is a property of the ensemble algorithm itself, not so much a property of the individual classifiers, it's difficult to correct. The one attempt at correcting it are these weights, and people still write PhD theses and nuanced weight mechanisms to try to figure out the best way to prevent this overfitting. But this problem is bad even if you have clean data. If you have noisy data, it's even worse, because boosting really, really, really wants to fit your noise. Because this guy, this mistake here, this guy that was mislabeled red, is so far away from the rest of the reds, you're always going to get it wrong for any surface you have. So boosting is going to really kill itself to put a garden of partitioning around that one mistake. And then any green guy that actually shows up in there is going to be misclassified later. OK, so if you really have clean data and no noise, boosting isn't too dangerous. The proof that ensembles don't hurt doesn't apply to boosting, incidentally, so that's another thing to be worried about. If you really want to use some sort of accelerating mechanism like this, there's another thing you can do which is a little less dangerous, and it's called I-voting. And I'll briefly explain that. The algorithm is only slightly different. The idea is that, again, you don't have weights on your data points anymore. All you know is, does the ensemble to date get it right or get it wrong? So it's like binary weights. So that's what the blue and the green, the blue and the red mean. If it's blue, that means the ensemble to date got it right. If it's red, the ensemble to date got it wrong. Then you sample from here, and you use a method which is in the I-voting paper. But basically, well, I won't go into the math, but it's set up such that the impact is that the bags you result in are always roughly half hard cases, roughly half easy cases. So that's always the case here. So again, you're focusing on the difficult cases, but you're not focusing. You don't know how difficult it is, so you tend not to focus as obsessively on the noise. And you get some of the behavior, some of the sort of focusing behavior that you got out of boosting. But you can still, and also notice there's no weights because they're not necessary. Not only does the fact that there's no weights mean that this algorithm is a little less sensitive to noise, it makes this algorithm much more amenable to parallel distributed processing. If I had the same data set and I wanted to analyze it a bunch of different processors and build up my horde of experts in parallel, I can do that with I-voting because I can just majority vote the results I get. Each one individually is going to be working sequentially, but all the experts that come back together, I can throw into the same pot. I can't do that with boosting because the weights aren't commensurate. So my problems at Sandia are all about scaling. And so to the extent to which I use I-voting, and I do for reasons I'll explain later, I always use I-voting because I can combine the experts. OK. Yes?
How many experts do you choose when the data, the dimensionality of the...
Right. So I just got a beautiful question, which was, how many experts do I choose? And that's beautiful because that's the point of the next slide. One of the reasons that boosting looked like it was better than bagging is because people weren't, in fact, building their ensembles to the appropriate size. And in fact, there's been a number of papers where people have published new ensemble methods, haven't evaluated them properly because they haven't used the right size. And the only upside of that is that it's given me a chance to write 3 papers by now, sort of pointing out, well, I'm sorry, but if you actually do the analysis correctly, it turns out these algorithms are equivalent. And it's also a practical question. How big an ensemble to make? You just want to know that. You don't want to have to tune that as yet another parameter. One of the beautiful things about ensembles is that there are algorithmic answers to most of the tuning parameters. And for the size of the ensemble, there's something called out-of-bag validation. It's not a parameter you have to tune. You can derive it from the data. And here's how you do it. OK, so first, don't use fixed ensemble sizes because they can be deceptive. This is, again, an invented example. But what you can imagine is that the blue line is a boosting algorithm, and that the goldenrod line is a bagging algorithm. And this is, in fact, what happened early in the ensemble field. People would take their training data, they'd build 100 experts, and they'd say, well, that's a lot, because that's 2 orders of magnitude more than 1. And what they wouldn't realize is they were exactly in this regime. They say, look, boosting is more accurate than bagging. Wow, I'm going to use boosting. So all boosting actually buys you is it gets you a certain level of accuracy earlier with a smaller ensemble than bagging will. But for most techniques, and certainly for decision trees, which I use, the size of the ensemble has almost a negligible impact on the cost of using the ensemble. And when you actually go all the way to the appropriate ensemble size, everybody evens out. So bagging is more robust. And when you get to the appropriate accuracy, when you max out accuracy, boosting and bagging roughly have the same number of members in the ensemble. So the apparent advantage of boosting and other techniques really only holds if for some reason you're constrained to a very small ensemble size. OK. Question, yes?
From this graph, I didn't see that bagging is more robust. Seems like means the levels off, all the curve, like accuracy is the same. I didn't see
Yeah. Yeah, so the question is that there's nothing here that indicates that bagging is more robust, and that's absolutely right. What I was referring to was that bagging does not have the vulnerability to noise that boosting does that I illustrated earlier. So this particular graph is assuming clean data. Okay. Now, you would think that it's obvious and easy to figure out how big a data set to make, how big an ensemble set to make, because every time you add a member to the ensemble, your accuracy is going to increase. So you just watch that until accuracy levels off. That's absolutely true. That's exactly what you do. The trick is measuring accuracy. That's the subtle part. It's not permitted to use your own training data to test the accuracy of your ensemble to date. I mean, you can. It's called the resubstitution error estimate. But using that is called the resubstitution error because it's a bad thing to do. It gives you very, very broad error bars, and they tend to be biased on one side or the other of the truth, and that bias tends to be a function of the data you're working with and the class mixtures and so forth. It gives you a very bad estimate of what the accuracy is. It's a bad thing to do. The other thing you can do is you can use a validation data set. You can take your training data, carve off 10% of it, set it aside, don't use it to train with, and then use that to evaluate accuracy. That's perfectly legitimate. The only reason you don't do that is that, well, now you're training your data only 90%, you're training your ensemble only 90% of your data. So what you're estimating is the accuracy of your ensemble if you only get to use 90% of your training data. Maybe that's less than your actual accuracy, and if you're going to use this in some place, if you're deploying this somewhere, you actually want to know what the best possible accuracy is. You can make an entirely separate validation set, but in general, ground truthing is expensive. It requires humans. Almost all ground truth either comes with people making these judgments, or you have some automatic mechanism which is noisy. And the issue about how to deal with noise in your ground truth is something I actually study, but I won't be getting into in this talk. Happily, ensembles and ensembles only give you a magic answer to this question too, how big an ensemble to make, and it's called out-of-bag validation. And here's how it works. Remember that every classifier, when you do bagging, is lacking some fraction of the samples. So here's that a little more clearly. Sample 2 was not seen by experts 3 and 4. That means it's fair for sample 2 to be evaluated by experts 3 and 4. The fact that every classifier lacks a fraction of the samples means that every sample is not seen by a fraction of the classifiers. The properties are dual. So sample 4, in this made-up example, wasn't even seen by experts 1, 2, 3, and 4. So I can use those experts to evaluate the accuracy samples 4. So as long as you keep track of which samples were seen by each expert, and that's just a little bit of coding, it's not hard, when you have to evaluate the value of an ensemble of size 100, well, you just take the first sample, you find out which experts I can actually consult, you consult those, you find out if you got it right or not, and so on. And you can build a perfectly valid, perfectly unbiased estimate of accuracy using out-of-bag validation, using the experts which are out of the bag for that particular data point. Okay. So, so we know what ensemble algorithm to use, which is bagging unless you're really, really a risk taker. And we know how to make how big to make the ensemble. The question is, are we done? And the answer is no, because there are some popular machine learning methods that resist the charms of ensembles. If you're using an unstable classifier, by all means use bagging. But if you want to or you need to use what's called a stable classifier, you have to do something else. Bagging by itself doesn't cut it. But there is an ensemble method that will apply. And for instance, some examples of stable classifiers that are important are support vector machines and conditional random fields. Both of those have a lot of applicability in the text analysis world and would be left out of the ensemble party if it wasn't for the algorithm that I'll be mentioning in a moment. So I first have to explain what stability is. Remember that one of the reasons ensembles work is diversity. This is just a reprise of the earlier slide. We want to have as much diversity among the classifiers as possible. Well, in the bagging context, unstable means the same as high variance error, means the same as likely to give you a diverse classifier. So what I'm illustrating in these examples is that I've got the upper right, I've got a few toy data points, a made-up partition that comes from it. In the bottom right, I've subtracted one red X and added one new one. just to illustrate the point that a decision tree, for instance, will just completely rechange its optimal partition based on that small a change in your sampling. And if you don't use pruning, which I'm going to argue later that you shouldn't, that's even more the case. I mean, you can get very big changes in the partitions from a decision tree by making small samples, changes in your sampling data. And in fact, early on, before ensembles were well understood, this was considered to be a disadvantage in decision trees, which absolutely it is. You don't like the idea that your sage is going to be sort of carving up space differently depending on whether or not you make small changes in your data. But for ensembles, this is beautiful because I get really diverse samplings of all the possible classifiers out of decision trees. The contrary example is stable algorithms. So here I'm faking a k-nearest neighbor algorithm where the algorithm is, for a new data point, you just look in feature space for the three closest other data points, and you let them vote as to what your current class is. K-nearest neighbor is well known to be a wonderful thing because it's actually the most accurate classification method. It goes faster to Bayes' error in the number of your training points than any other method. But it's completely impractical because it actually isn't a classifier. You actually have to carry your entire data set around and consult it every time you want to classify a new point. And it is also the canonical stepchild of stable algorithms. If I make that same small change, decision surface changes a little bit, but not very much. OK, so the question is how to bring the magic of ensembles to stable algorithms. So again, let's reprise the idea behind bagging. Bagging took this table of data and looked at it in a row-centric fashion. I chopped and rearranged it by row. And so in this particular case, for instance, Q3 is missing, Q2 is shown up twice, and so forth. Well, the algorithm that will give you, that will bring ensemble-like properties to stable algorithms chops by column instead. In other words, you use all the data, or actually, practically, you use bagging and random subspaces together. But the core idea of random subspaces is that instead of letting myself look at all the attributes that describe my data, I pick 2 or 3 of them, just a tiny fraction of them, and I only look at those. So on the face of it, that looks like a really terrible thing to do, but then again, so did bagging. I mean, what I'm doing is I'm taking 30 attributes, and I'm taking 3 at random, and I'm projecting down into a 3-dimensional projection of my original 3-dimensional space. But then I can repeat this process, of course, whoops, and repeat this process and repeat this process. And this takes things like support vector machines and conditional random fields and such not, and makes them diverse enough that you can apply ensembles. The proof of that this never hurts does not apply to random subspaces, but there's also a bounty out for the first person who can show that it has hurt, and that bounty hasn't been claimed. There's a question here? No. Excuse me, the question was, do you need to know anything about the independence of the columns? You don't, and that's a good question. In fact, I want to say a couple of things. One of the usual data mining ideas is that if I have 30 columns of data, 30 columns of attributes, well, quite often some of them are correlated. It used to be the case that people would say, OK, well, I'm going to take the correlated ones, I'm going to toss one out, or I'm going to come up with some feature that combines the two and decorrelates all my columns from each other. And the reason people did that was something called the Curse of Dimensionality, which says that as you have more ways to describe your data, you have to have that many ways squared or more data points to get statistical significance for any given machine learning algorithm. Ensembles, among their many magic properties, get around the Curse of Dimensionality. In fact, because you're, again, trying to get diverse behavior out of all the individual classifiers, the fact that you have too many attributes for statistical separation doesn't make a difference. The crucial point is that you still have to use out-of-bag validation to get your ensemble to the right size. But if you do that, having a low-order description still works and works beautifully. So my advice, if you're doing machine learning, is throw in everything you can think of. The only constraint on what you use as an attribute should be the cost of measuring it in the first place. There's no reason to be, you think about crazy stuff. There was a famous problem where the UPS was trying to figure out if there was any correlation, if they could predict which boxes would break as they shipped them, so they could figure out what boxes to give extra attention to. So they measured height and all the dimensions and weight and what the person valued it at and what their history of valuing it as was. And they put all that interesting stuff in. It turned out, just because of the way they did the database query, zip code showed up in there as well. Zip code was the #1 predictor. And the reason for that is it turns out that all the people who make Crystal, or all the people who make, delicate Fabergé kitty cat things, have factories in a particular zip code, right? So people were actually shipping to and from particular zip codes, and those were the places where people were making claims against their data. Well, the other factors did make a difference, but zip code was the #1. So the lesson there is, don't pre-filter. If you've got it measured and you've got it written down, stick it in, because you might be surprised. Okay, the other question in the back, yes? I'm sorry, I couldn't quite hear you. Right, so you can't do, the question is, can you do out-of-bag validation in this context? Thank you. You can't do random subspaces by itself. So typically people do combine bagging with random subspaces for that purpose. The bagging doesn't typically buy you any extra accuracy, but it does tell you when to quit the ensemble. And the other reason you might use bagging is this. If I have only 8 features, and I'm going to pick them 3 at a time, 8 choose 3 is a small number. I can't do it in my head, but it's a small number. So your ensemble is going to have maybe 40 cases in it. Maybe that's not enough actually to explore the entire space. So by combining it with bagging, you get a little bit more diversity. Okay, the other thing you can do is rather than random subspacing your data, you can just say, with a stable algorithm, you can say, fine, I'm just going to use the stable algorithm as is. I'm going to build a bunch of sages. I'm going to let my support vector machine see all the data. I'm going to let my neural net see all the data. This is called the combination of strong classifiers. You can start looking at this in the literature. What I'm mostly talking about in this talk is ensembles of weak classifiers, but there's a whole different subthread of strong classifiers, and maybe some of the classifiers are people. You've got a couple of computer processes making some decision, but you've got Wendy and me in a ConOps center, and we had a vote as well as to what the outcome of this thing should be. The problem is that majority vote is no longer the best way to combine all this. In fact, it's rarely the best way to combine all this. And so you have to do a fair amount of work to figure out what the right combination rule is. A lot of people have published lots of things. And it turns out, of course, that you can machine learn this. You can take all your original data, you can take the outputs of your experts, add them to your feature vector, and build a neural net or a decision tree that tells you how to combine them. And of course, once you've done that, the worm can eat its tail entirely, and you can build an ensemble of decisions that tell you how to combine these guys. And people have practically done that. I used to do this kind of work. I don't anymore because it doesn't scale. I need algorithms where I can not think about the tuning parameters, and I need algorithms, well, it just doesn't scale, so it doesn't work for me. Okay. So, hey, it's disco time. And speaking of scaling, up to this point, you may be thinking to yourself, well, ensembles are cool and all that, and they're going to give me some accuracy, but they're obviously massively impractical. Because each bag is basically replicating your data. You can do clever coding, referencing tricks, but basically, theoretically what's going on, if I have a terabyte of data, and I often do, and I bag it, I've generated another terabyte of data. If I bag it again, I've generated another terabyte. If my ensemble grows to 1,000 members, I've made 1,000 terabytes of data in order to build my classifier. Well, Sandia's got great computers, but we can't quite do that. So there's something else you can do. This is actually the core of my focus at Sandia, is how to go about scaling to huge amounts of data. And there is an answer. And the answer is bozos. This is the Sandia contribution to the field. And this gets back to the question somebody asked earlier about whether or not the bags have to be the same size as the original data. This is another aspect to that answer. What you do with the bozos is you say, OK, I can't show all of my data to each bozo. So I show a tiny, tiny, tiny fraction of the data to each bozo. Each individual bozo, as a result, is much less accurate than the expert, which is in turn much less accurate than the sage. But the horde of bozos It's provably no worse than the crowd of experts, which is provably no worse than the sage. To make this work, you can't just pick random tiny subsets. Well, I'll take that back. You practically can, but you do get into a heat death of the universe situation where the size of the ensembles is just way too big to actually practically work with. But luckily, you can do something else, and what the term bozo refers to is the small sample version of the I-voting concept. So this is I-voting again, where I am picking the samples so that each sample is half hard cases, half easy cases. But now I'm picking a tiny fraction. Here I'm showing 4/10, but in real practical problems, I pick as many samples as fit onto the processor I'm working with. And depending on the problem, that could be 1% of the data, it could be 10% of the data, it could be 1/10 of 1/10 of 1/10% of the data. Now I am using I-voting, which I warned you against earlier, but it turns out that in the small sample case, all of the dangers go away, because the odds of obsessing on a particular data point from run to run go close to 0 because you're looking at such a tiny fraction of the data. You can't obsess on challenging cases. There's a question.
Do you lose the ability to parallelize this though if you have to use I-voting for fully bothos?
So the question was, what's the impact on parallelization? And no, the answer is no, that you don't lose the parallelization. You do run into a situation where So there's an interesting aspect to that question that I don't know how to answer yet. So if you come up afterwards, maybe we could talk about it. But the core answer is that you can actually just take your data, let multiple processors look at it. They all grow their trees. They all feed a certain amount of information back to a root node, which is keeping track of the accuracy of the ensemble. At some point, you quit. It turns out if you do that, you do a little bit more work than you would have done if you hadn't parallelized, but you do less work than you would have done if you'd done it serially. So this is beautifully parallelizable, and this is, in fact, this is how I use it when I do practical work at Sandia. Okay, so yes, question.
Do you need more bozos than the number of experts?
I'm sorry, just couldn't quite hear you. What's the question again?
Do you need more bozos than the number of experts?
Yes, you do. Yeah, absolutely. It is practically the case that the question was, do you need more bozos than you need experts? The practical answer is that practically, yes, you do. If you don't, it turns out you have a simple problem. But again, the limit point of all these techniques turns out to be roughly the same. So we are essentially done. Incidentally, if you go looking for this work online, I've got pointers at the end of the talk, but we call these bytes rather than bozos when we publish. Partly because the San Diego Legal was concerned about actually dragging in a copyrighted figure. So it's small bytes of data. Okay. So maybe you want to run out and start coding now. The question is, how do you get started? Well, you're welcome to contact me. I'll talk for 15 minutes to anybody. One thing you can do before you talk to me, and even for your own benefit, because it's the first thing I'll ask you to do, is actually prepare your data for machine learning. Think about it in the context of the way I've been talking about it, and just try to lay it out. Because it turns out every time I do that, even on problems I think I understand, I realize there are assumptions and idioms and things I learn about the data in the very process of trying to set it up. In fact, as a rule of thumb in the data mining world, that 80% of any of the effort, of the cost, of the time of any data mining project is preparing the data ahead of time. There's some background reading, which I'll point at. One of the pieces of background reading I suggest looking at, if you really are going to get into this, is learning to evaluate ensemble algorithms against each other accurately. I and my colleagues ended up taking a 6-month digression from actually working on ensemble methods and making them parallel to working on how to evaluate whether or not you really have statistically significant differences in your ensemble results. It's a tricky problem, but I think we've written it up in a cookbook fashion anybody can use. It's in PAMI. That's what reference 3 points out. More and more open source software these days has ensemble stuff built into it. I have software myself, which will be hopefully open source by the end of August. But as you can tell from the blue words, I have one more bit of advocacy to tackle, and I've got 5 minutes to do it in, so I'll tackle it. which is if you don't have a prior investment, if you really are going to start from scratch, you've listened to this talk and say, oh, good, I'm going to go machine learn something myself now. The techniques I recommend are to use decision trees over other pattern recognition methods. And if you're going to do that, to use a specific ensemble method called random forest that works only with trees. Now, this is a fairly controversial thing to say because there's actually something called the no free lunch theorem that says that all pattern recognition algorithms for a given set of training data should come up with roughly the same result. And that theorem is true for clean, noiseless, and what's more, correctly normalized data. The issue is that if you have, like for instance, in the UPS problem, they had weight and height as two different attributes they were working with. Well, most pattern recognition algorithms use a sense of a distance metric and attribute space to figure out how to partition attribute space. I mean, this point is going to be called blue if it's closer to a blue circle. It's going to be called a red X if it's closer to a red X. Closer presupposes that you have a distance metric. If you have a distance metric that depends on your axes, and you change the scaling of your axes, you can come up with different conclusions. This is what I'm trying to illustrate with the example on the right. The little question mark looks perhaps closer to a goldenrod circle than a green X. The upper figure, it looks definitely closer to a green X in the lower figure. All I've done is change the scaling of my axes. All I've done is decide to measure height in feet rather than inches or vice versa. Almost every pattern recognition machine learning algorithm falls prey to this, except for decision trees, for a reason I'll explain on the next slide. Other nice things about decision trees is that if you know something about decision trees, you might be saying, well, what about pruning? Pruning is where the art of making decision trees work. Turns out if you're going to use them with ensembles, you don't have to prune. You grow trees out to a pure level, and all that art, tuning stuff goes away. Decision trees also have the ability, for reasons that will be clear when I talk about this slide, to entirely ignore noise. Earlier I told you, look, throw every single attribute you want to into your mix. I should have caveated that because that's really only true. That's only a non-dangerous thing to do if you're using decision trees. If you use neural nets or anything else that pays attention to a distance metric, if that new attribute looks like, for some subpopulation of the data, has any value at all, the neural net's going to try to give some weight to that noise metric. Decision trees have the property that the only time noise can hurt you is if that noise value turned out to be statistically more reliable than all your other attributes, not just one of them, which practically never happens. And the way it does this is this. I'm going to give you the 30-second explanation for how decision trees work. Let's imagine I have all of that data without any partitions. Well, I've got X and Y. I'm going to measure purity. Right now, this is a fairly impure mix because I've got red and blue. What I want to get to is a situation where all of my partitions are pure. So I can start here, and I can say, well, if I make a threshold here, does that decrease my impurity? Nope. If I make it here, well, now I've got a pure red X, but I've got a pretty mixed bag over there. If I make it here, I'll make it here, make it here, and so forth. So you have some measure of impurity decrease. You look at all the possible X thresholds, and you look at all the possible Y thresholds. You figure out the one attribute and the one threshold that gives you the best result, and that's the top branch of your decision tree. So now I've partitioned my data into two pieces, and you recurse. This guy's already pure. I don't have to do it again. This guy is mixed. I repeat the process. I get another partition, and so forth. So what that means is, since all I'm asking myself is where does each guy fall on either side of this line, I can scale the x-axis any way I want to. If I stretch it out, the ordinal relationships, the order, is exactly the same. So decision trees are invariant in the scaling of the axes. So if you don't know that much about your data and you don't want to worry about how to normalize weight versus height, it's a wonderful thing to do. If you do insist on normalization, there are techniques for doing that. There's something called the the M distance. It's written out in my slides, so you can look it up there. That even the M distance makes assumptions about normal distribution of your data and so forth. I mean, decision trees are non-parametric, make no assumptions. They're beautiful. And So here's how random forest works then. Remember again that we have, this is an example of this is the original data, the full data set. And what's going to happen with decision trees is that when I build my first split, and with random forest, when I build my first split, I do random subspaces for that split only. So I let myself look only at freshness and distinctness, and I figure out what the best split would be. But when I make the second split, I pick a different set of attributes, figure out what the best split would be, and repeat. So this is like, with random subspaces, you pick one set of attributes, you build your entire classifier. Here, I'm repicking every time I go. Now, you ask yourself, why the heck would you want to do this? Well, you don't do it for accuracy. Because it turns out that if you build out to out-of-bag validation, a random forest set of trees is going to be no more accurate than a bagging set of trees. The reason you do it is computational speed. For decision trees, how long it takes to build a tree is directly linearly proportional to the number of attributes you have to work with. So if I've got 30 attributes and I look at 3 at a time, I've sped up by a factor of 10. And in many popular bioinformatics applications, you might have thousands of attributes. If you look at 10 of them at a time, you get a massive speed up. And in fact, speaking of speed up, and I'm about done, I'm going to tell you the final insanely implausible but true thing about ensembles, and in particular ensembles with trees. So, like I said, trees are order A n log n, where n is the number of training points you have. Now, you may remember when I was talking about doing bozos that you look at a tiny fraction of the data, and the ensemble of bozos, if you grow it to the right size, will be more accurate than the sage. Well, what the n log n tells you is that trees speed up faster than linearly as the training set size shrinks. So it is theoretically, and now in my experience, practically possible to build an ensemble of 1,000 random forest bozos using I-voting, because you can combine I-voting and random forest without any difficulty. They're two orthogonal approaches. You can build an ensemble that's more accurate to the sage, build it out to this limit, faster than you could have built the single sage. In other words, this technique can give you a black box, which is more accurate than the sage and was generated faster than the sage. Now, it's not always the case. Depends on the nature of your data. But for really big data, but it becomes more likely the bigger your data sets. And most other algorithms are worse than algorithms are worse than A n log n. SVMs and neural nets, in fact, have convergence properties that benefit from this property all the more. There's a recent paper on a technique called Boost SVM, where the core point wasn't to make SVMs more accurate in an ensemble. It was just to be able to build a group of SVMs in practical computational time. Their data was so big that it would take in the heat death of the universe before they could actually build a single SVM over it. But by beating on it, they could get close to the same accuracy by looking at smaller samples. So I think I am done. If you use supervised machine learning, and who wouldn't, because we all want to predict the future, if you have clean data and you're a risky sort of person, you can use I-voting or boosting. Otherwise, use bagging if you can get away with it. If you have to use a stable classifier, then consider optimizing your small ensemble or using random subspaces. You have a huge amount of data, use bozos, combine bozos with random forests. But whatever you do, let the data tell you how big the ensemble ought to be. Don't set it to some arbitrary value, because A, you won't get as much accuracy as you could, and B, you may draw incorrect conclusions as to the relative merits of your approaches. And that's it. Thanks for your attention. I have both a few minutes for questions and also just for chatting afterwards, so yes. Are we being kicked out of here at 3? Wendy, do you know? No. OK, so.
Can you make any recommendations for learning ranking using ensembles?
Yes. But it's not a particularly novel one. Well, OK, there's lots of things you can do. You know about board accounts? No, OK. So the classic best property for combined, so what I'm assuming you're saying is that I have one guy who's giving me a ranking, an ordering, somebody else is giving me another ordering, somebody else is giving me another ordering. I want to combine those orderings in an optimal way. Well, the way to do that was figured out in the 17th century. And And I actually have a reference to him, number 6, a guy named Cortese. And it's a technique called board accounts. And it turns out that there's lots of interesting properties of board accounts, but it works kind of like this. If ranking indicates your dissatisfaction, your increasing dissatisfaction with an alternative. So in other words, I put if my third, well, you can see the point. I mean, I'm going to get more and more dissatisfied down the pile. Using board accounts, which are a very trivial algorithm, to combine them, provably gives you the least group dissatisfaction out of the combined ranking. And in fact, I discovered board accounts without knowing what they were when I was a kid, and my family would fight over what movie we were going to go see. We'd all rank our movies. We also got one veto. I'm not going to see Mary Poppins again. And then after the vetoes were taken out, we would board account our data. What happens with board accounts is basically this. If you have 10 alternatives, every time I rank something 1, it gets 10 points. If I rank it 2, it gets 9 points. Add up all the points, rank by the points. It's a beautifully robust technique. Question over there, yes?
I was also going to ask about the voting method.
Okay.
I mean, in addition, there's plurality.
Right, majority vote, right?
But there's a whole ton of other.
Yes, absolutely. So the question is, why majority voting as opposed to lots of other ways you might combine matters? Well, right. So the short answer is, I can't respond to all of them, but here's the rule of thumb. If you're going to use optimized classifiers, and as in that one slide I used, it's quite possible that any variant of voting you can think of might be the right thing to do, and you really do have to look at them. In fact, some people have looked at the question of the combination rule as an optimization problem. You look at all the possible weights, and in fact, I have a colleague at Notre Dame, Nitesh Chawla, who's done a lot of work there, and he and I are writing a paper about this. But if you have a huge horde of weak classifiers, which is the thing I've been talking about mostly, where all of the classifiers have used the same core algorithm to generate their partitioning, but it's just been varied by various ways of looking at the data. Nothing has ever beat majority voting. There's not a proof around that yet, but every time I've tried, or every time somebody's written a paper that suggests that something other than majority voting is better, as soon as we've drawn it back out to out-of-bag validation levels, it turns out that the apparent advantage goes away. There are some, in fact, if you want to do that, a better thing to do is what's called ensemble pruning. Rather than weight your ensemble, you can take the entire ensemble and you can begin throwing members of the ensemble out, throw out the poor performers. But you have to be careful about that. So that's sort of like binary weighting. I'm going to weight some of these guys 1, I'm going to weight some of them 0. But it turns out that it is also really easy to destroy your diversity if all you do is throw people out based on accuracy. In fact, the most successful pruning algorithms that I've seen, successful in the sense of how well they do on entirely independent validation data, have pruned not based on accuracy, but on diversity. They've deliberately left classifiers in that were less accurate overall, but had some particular part of the feature space that they had focused on, which wasn't well looked at by the training data that you had, but turned out to be matter when you looked at the entire universe. Question back there, yes?
Going back to the idea of using full unpruned decision trees for your ensemble classifiers,
Uh-huh.
I want to look at it in terms of computational cost. I guess you could try and build just a partial decision tree, be faster to build, but then you will end up with more experts you need into your ensemble. Right? People looked at this kind of trade-off in terms of how strong you have to build your individual.
They have. The term to Google is decision stubs. And so I don't know of any proofs around this yet, but the issue is this. I've looked at decision stubs a little bit myself. So the idea, the question being asked is, what happens if instead of growing my tree out to the full extent, I do something else, which is to say I take the first 2 or 3 cuts and then I quit. So I've made a very crude approximation of a partitioning of the space. So the problem is this. First of all, decision tree stubs tend not to be very diverse. So you do need a lot more of them to get to the same accuracy. And sometimes they are so not diverse that if you don't go down far enough, if you don't go down to at least 3 splits, they all line up behind the same problem. And where that particularly hurts you is in something called the skew problem. I haven't addressed this here, but one of the issues is what if, and this is something I deal with all the time, what if my data, my training data is such that 0.1% of the data is actually the class I care about. 99.99% of the data is the other class. Unless you take care, any given classifier is going to say, well, I'm going to learn the trivial classifier that everything is normal, and that's going to be 99.99% right. So it's not going to understand why you're upset with it. There's ways around that, but decision tree stubs fall into that trap almost immediately. In fact, they fall into it even if you have, in my experience, like a 30-70 split of your data, because they just fall into this. If you don't go down far enough, you don't get into the 30% except for very randomly, and you hurt yourself. And what's more, although the calculation of decision trees is worse if you go all the way out, most of the reputation decision trees may have had for being time-consuming came from the pruning. If you actually just go all the way to the bottom and you don't prune, it's a very efficient algorithm. And the other thing nice about it too is that you can predict exactly how long it will take to build a decision tree for a given data set and number of attributes, which isn't true of anything that iterates, SVMs or neural nets. Question? Well, it depends on what you're trying to do and how you're going about it. But if you're talking about a situation where you've got microarrays and you're going to take as the core features the degree of expression for all of these other genes, and your truth is, was cancer type A, cancer type B, people have had very good success, in fact, with ensembles of random forests. There's some prior papers that have done exactly that. So the trick with that kind of problem is that you do have thousands or millions of features depending on the size of your array. And many of them are uncorrelated, and some of them, because of just mistakes in taking the array, are wrong or noise. So either you have to do a fair amount of analysis up front to kick those out, or you have to use something like decision trees, which are robust. But that does raise a question, which is this. That's going to be very unsatisfying to any biologist you're working with, because there's no explanatory value in the resulting ensemble of trees. They don't get to look at the fact that, oh, I see gene 513 is always dominant, and port 7 is low, and so forth. And that's absolutely true. I don't have math around this, but I'm evolving the position that there's now a Heisenberg uncertainty principle between the two things you use machine learning for are either to have an accurate black box that tells you really what the label is when you throw in the data, or you have something that's going to help you explore your data, understand better what the trade-offs are, what matters. People used to think that those two things were achievable at the same time. And I think there's a direct actual conflict and trade-off. If you give me an explicable machine learning algorithm, I can probably make it more accurate at the cost of making it completely non-understandable, usually just by putting it into an ensemble context. Question?
I was curious about that because one of the features of random forest that the brain like touted was like it's kind of a gray box. Like you can look inside and get aggregate statistics on which features
right.
are more important by looking at each individual base classifier.
Right, that is true. So what the questioner is referring to is the fact that the guy who came up with random forest in the first place pointed out that you can manipulate random forests in a certain ways to give you some sense of the relative merit of features and pairs of features and so forth. And the way you do that actually is quite interesting and clever. Let's say I have 30 features. I grow my ensemble, use out-of-bag validation. I use all 30 features. Now I take one column of those features, and I reorder those values across the samples. I'm not injecting noise. So the column still has the exact same statistics, the same mean, standard deviation, but I completely decoupled the actual value of that feature from which sample it belonged to. Then I use that exact same algorithm to grow another random forest. The delta between performance gives you a measure of how relevant that feature was in the first place. If you can scramble its brains like a salad and it makes no difference, well, that feature wasn't buying you much. If your performance drops off, it does. The danger with doing that is the same danger with any feature selection mechanism, which is the pairing problem, which is that the best two single features are not necessarily the best pair of features you would want in the tree. In fact, it's quite often not the case because of correlations and such not. So if you really want to figure out what the best subset of features is, you have to use forward feature selection or exhaustively try all the possibilities. Breiman's technique gives you a way of doing that in the random forest context, but you still have to do the hard work of looking at every possible combination and figuring out what the best subset is. And I guess it's also the case that Breiman was able to show that either Breiman or Friedman showed that the ultimate accuracy still doesn't get any higher, even if you click down to the right features. The only value is by telling, you can tell a human, look, gene 13 is by itself the most explanatory gene. Anything else? Oh, question here.
So Rich Caruana at Cornell actually did that experiment where
What?
you built these enormous ensembles of all these different kinds of classifiers.
Okay.
And after some certain amount of tweaking, it gets much better performance, of course, on all these different kinds. So my question is, I mean, if these ensemble methods pretty much always help us, and they always pretty much get us really good performance, is there anything left then in traditional classifiers? Is there anything we should be looking at building new classifier methods?
Yes. So there's, okay, great. So here are the two main problems that I'm wrestling with. And I can imagine, actually, that both of these might be relevant to Google. And I mean, I don't know. As long as there's hungry professors, there's always going to be an interesting problem to work on. But one of the issues is that I mentioned random subspaces as a way of bringing ensemble properties to stable classifiers. It's certainly the current best way, but I don't think anybody necessarily believes it's the best and only way anybody can come up with. In fact, there's and so people keep publishing and coming up with variants on the idea. I was at there's a conference, I think I mentioned it in this talk, every couple of, how to get started slide. There's something called the multiple classifier, I think I just accidentally activated iTunes by, the top button of my remote brings iTunes up and I have no idea why. It's just Apple saying, Okay, so there's the Multiple Classifier Systems Conference, where a lot of the cutting edge research happens. And I was there, it was in Prague this time. I was giving a talk a month ago. And somebody had the great idea of, well, one way to get more diversity out of the random subspaces idea is not only take that projection down into project down into a three space, but then use principal components analysis or something to randomly rotate, or just randomly rotate it. Right? I mean, every time you get a different view of the data, and that's one way of generating diversity, and they showed some initial results, although unfortunately they didn't use out-of-bag validation, so I raised my hand. So one of and the reason this matters is that, for instance, a problem I am working on is word classification in the sense of there's something called named entity recognition. You have a paragraph of text, and you want to, for every word, say that word is a person, place, thing, date, or other, right? So you're analyzing business data, maybe business news stories. So it's a classification problem. It's well studied. The current best state-of-the-art algorithm for doing NER is conditional random fields, and I'm convinced that really is probably the best approach. But conditional random fields are very stable and really resistant to ensembles for reasons I haven't gotten into. And so, the best way to take ensembles to CRFs is a new area of research. But to change, so that's one idea. The other idea is this, and this is the thing that I work on the most. It's a core assumption of machine learning that the future resembles the past. That the data you're going to apply your classifier to is statistically similar to the data you learned it on. Well, I have data sets that are so large. So a lot of what I work on is analyzing simulation data. Sandia does a lot of safety studies. We design all the containers that carry nuclear sludge around. So we have analysts that will simulate one of these containers, and these containers have, are containers within containers within containers, and they'll simulate, well, what if this container is on a plane, and the plane gets hit by lightning in a storm, falls, hits a bridge, hits the frozen lake below it, fuel spills, and the fuel catches on fire. Now, that sounds like completely paranoid, but it turns out that's what our safety engineers are. And that particular scenario happened to a mail plane in 1963. So because it could happen, it's like the limit point for these safety studies. So we do these huge safety studies. They're all simulated because we can't actually hit planes with bolts of lightning very often. And they're so big that the data gets partitioned. I mean, I don't know how much you know about mod sim, but basically the idea is that if I were to simulate this room and simulate what happened if I burned it and people ran out screaming, this corner up there would get a mesh devoted to one processor, and this corner would get a different mesh, and this corner would get a different mesh. So the room would be split up and handed to different processors, each of which would do the simulation on its own and communicate only as much as it needs to. Well, if I'm trying to learn something about the flame properties of the backs of those chairs when they burn, well, I'm not going to learn anything about that from the processors that are working up here. So in other words, all of my different processors are seeing an inhomogeneous mixture of my training data. But so I can build in a different ensemble from every processor. That's easy. But later, I don't get to know which processor to use, because if I use this data later, it might be, when I simulated the burning, maybe that's 10,000 processors. When I do the processing later, maybe 1,000 processors. The way the room gets split up is totally a function of the convenience of the load balancer and has nothing to do with the convenience of machine learning, which is almost always the case. So I don't get to know where in the room I am. So I have to figure out some way of combining the opinion of processors that never saw burning chairs versus processors that saw nothing but burning chairs and screaming humans. So working out how you go about combining data that was taken from statistically inhomogeneous populations is a real mind bender. We've published a couple of beginning papers, but I just don't know where it's going to go from there. I mean, you can get the ensembles to try to self-assess. I have a different talk, actually, I gave about a month ago exactly on this, and if there's some pressure, I'll come back and give it a Google. Anything else? Yes?
You mentioned some theory that shows that at least, like the Dr. Wolf, you can't do wheres.
Right. I'm sorry, go ahead. Yeah,
can you be more specific?
Yes. Well, I can't do the math off the top of my head, but basically the theorem says that if you resample your training data, basically if you use pure bagging, and you use pure bagging and you use out-of-bag validation, and that the sage was better than randomly accurate. In other words, so this theorem doesn't apply if your data is so bad that even the sage is guessing wildly. But as long as the sage is slightly better than random, and you bag, and you grow the ensemble out-of-bag validation, the ensemble will never do worse than the sage. That's basically what the proof says. There's, and it's in, I think it might be in one of these, wake up. I believe it's in reference 4. Anything else? Yep. One more. No, sorry, one more. Feel free to filter out at any point. I won't be offended. Oh.
Would decreasing the dimensionality data to make creating bozos faster with less columns?
So you're asking if decreasing the dimensionality data makes bozos faster? Yes. So I think what you're asking is, can you combine, for instance, the random forest idea or the random subspaces idea with the bozos idea? And you absolutely can. In fact, in practice, what I usually do is bozos, which means I voting with subsamples and random forest. The combination just screams, at least for my data. OK, thanks so much. That was a bunch of really intelligent questions.